in this lesson, we're going to solve this problem. This problem, it's a gradual loading. It's under the strain energy. Here, we're given a diameter and its length, another diameter and its length. That means it is a two-section bar. So also, we're given the force, which is a compressive force, and the Young modulus. Here, we're asked to calculate the total strain energy. So here, we've got the common here, which is force. It is 1.5 kilonewtons. This is 1,500 newtons. And we've got another common here, which is Young modulus, which is 200 gigapascal. This is 200 times 10 to exponent 9 Pascal. Then here, let us separate this side like this. Then, because here we've got two sections in this bar, we've got the section for this diameter of 100 millimeters, we've got the section for this diameter of 80 millimeters. So we'll separate here. We'll say the diameter for 100 millimeters, it's a diameter 1, which is 100 millimeters, which is 0.1 meters. Then we've got its length, this one 300 millimeters, it is 300 millimeters. This is 0.3 meters. Then also, let us separate the section here. Also, we have the section 2, which is the diameter 2. Diameter 2, it is 80 millimeters. This is 0.08 meters. Then we've got its length, say length 2, it is 400 millimeters. This is 0.4 meters. It is like this. Then let us calculate the area 1 from the diameter 1. Here it's the area 1 is equal to a pi. Then the diameter is 0.1 squared divided by 4. This, it gives the area 1 to be 7.85 times 10 to exponent negative 3 meter squared. That is the area 1. Then area 2, it is pi, and the diameter here, which is 0.08 squared divided by a 4. This gives the diameter 2 to be 5.03 times 10 to exponent negative 3 meter squared. That's the area 2. Then we have now these sections. Let us come to the first question here, which we're asked to calculate the total strain energy. To calculate the total strain energy, we have to apply the formula to calculate the strain energy. Here we will say a total strain energy, it is equal to, we write the formula for strain energy times the length divided by 2 times the area times Young modulus, plus, because we've got two sections on this bar, plus the force again times the length divided by 2 times the area times Young modulus. Then, because we've got two sections as we have separated here, then we'll say here we've got the length in this section. We'll say the length is length 1, and the area 1, we've got length 2, we've got area 2. Let us see now. We've got the force. Here it is. We've got Young modulus. Here is Young modulus. The length 1. Here it is. The length 2. Here it is. And also the area 1. Here the area 1 is. Area 2. Here the area 2 is. Let us substitute. That means we have all. It is, the force is 1,500. Then we put square times the length. The length 1, it is 0.3. That's the length 1. Then all divided by 2 times the area 1, it is this one. It is 7.85 times 10 to exponent negative 3. Then Young modulus 200 times 10 to exponent 9, like this. Then we plus for the second section. Here the force the same, it's a common 1500. Then the length here it's 0.4 divided by 2 times the area, which is area 2 is this one. It is 5.03. This is point times 10 to exponent negative 3. Then Young modulus, the common, it is 200 times 10 to exponent 9. Then this will give the total strain energy. In this side, we have 2.15 times 10 to exponent negative 4. On this side, we have 4.47 times 10 to exponent negative 4. Don't forget to put plus here. Then this, when you plus this and this, it's gonna give the answer to be 6.623 times 10 to exponent negative 4 joules. That is the total strain energy, this one. Then we have found the first question. Let us go to question number 2, which says find the total extension. That is a change in length. This one's a change in length. Change in length. Some other books say X. Then let us calculate it. So here they are looking for the total extension, of which is a change in length. Total change in length is equal to a change in length 1 plus a change in length 2. This, a change in length formula, it is a force times the length divided by the area times Young modulus. Then this will write under each section here, of which it is a force here times the length divided by area times Young modulus. Also here you plus here, force times the length divided by area times Young modulus. This means it's length 1. This means it's length 1, it's area 1. Length 2, it's area 2. Let us substitute because we're looking for a total extension. Let us substitute. A force is a common 1500. Then the length is 0.3. Divide by the area 1, it is 7.85 times 10 to exponent negative 3. Then the Young modulus is a common 200 times 10 to exponent 9. Then we plus here. Come to this section 2. Force is a common. Then times the length, of which is 0.4. Then divide by the area 2 is 5.03 times 10 to exponent negative 3. Then the Young modulus, which is 200 times 10 to exponent 9. Then under this section, we've got 2.866 times 10 to exponent negative 7. Under this section, we've got 6 times 10 to exponent negative 7. Don't forget to put plus here. Then when we add this, it's gonna give 8.866 times 10 to exponent negative 7 meters. Then this you can take it further to be 0.886 times 10 to exponent negative 6 meters. That is the final answer for the question 2. That's what the question 2 is looking for. When you want to calculate the total extension, it is a total change in length like this, then change in length 1, change in length 2 if we've got 2 section bar. But if you have 1 section bar, you just do this only. Then you substitute, you go to the answer. If it's 3 section bar, you will add another section here, which is section 3, to calculate the total change in length. Also here, if it was a 3 section bar, you will add another section, that is section 3. Add another section here, which is section 3. But if it was a 1 section bar, there was no necessity of this section 2. But here it's a 2 section bar. It is a first section, second section, because it's a 2 section bar. Also here, first section, second section.